So good morning, everyone. Thanks for coming to this session. I would like to start thank the Insper for the support and the first invitation to Professor Lars. So we have the great pleasure to have Professor Lars Peter Hansen. Professor, I am going to give a brief description of with my bias. Professor Lars is professor at the University of Chicago Booth School of Business. Lars has made many contributions to economics, which includes, as everyone may know, the GMM, the generalized method of moments in econometric models with the idea of minimal assumptions, asset price and macro indicators, models of uncertainty, financial crisis, robust control. Like I would like to highlight the very famous the Hansen, Jagannath and bounds, the contribution with José Shakeman, the term structure of asset pricing. More recently, the contribution with Tom Sargent about robust control and macroeconomics. Hansen has received many awards. Just to say a few, the Frisch Medal in 1984, the Everin Plain Neyman Prize in 2006, and the Nobel Prize in Economics in 2013. As Lars concluding his Nobel lecture in 2013, complicated problems do not necessarily require complicated solution, and I guess that we are going to see in this lecture wonderful contribution to the debate on climate change policies, the role of uncertainty and robustness in misspecification in using a social planning approach. Professor, the floor is yours. Thank you so much.
Yeah. Thank you for that kind invitation. I regret that I could not be there in person this time and look forward to my next trip to Brazil. I'm going to be talking about some research. It's joint with a variety of different co-authors, which I will not give them all the credit they do, but this is certainly very much joint research. And the title on this slide is really too narrow for what I want to talk about. I really want to be talking about uncertainty in policy. I will get to the specific aspects of stochastic responses later in my talk, but I really want to get at this more general question about how do we confront uncertainty in policymaking arenas and setups. Let me just go down. Sorry, So I'll just put a quote here from a recent paper in Nature. The economic consequences of many of the complex risks associated with climate change cannot, however, be currently quantified. I would want to substitute fully quantified. These unquantified, poorly understood, and awfully deeply uncertain risks can or should be included in economic evaluations and decision-making processes. I would certainly agree with this. This paper kind of lays this out there. They don't really provide a framework for doing this, and I want to talk about how we can start making some of these concerns operational. So here's what kind of is a bit haunting about this policy and why I think uncertainty is very important. There's this quote from Hayek's Nobel address that's about the limits of knowledge. And of course, Hayek's Nobel address is a very interesting read. It really challenges the sense in which economics is a science. It takes the field of econometrics and basically dismisses it as having contributed very little. It argues for mathematics as a language of clarity, but not for quantitative purposes. So there's many aspects of this essay that I would not fully embrace. But there's this one aspect that I really kind of like and certainly agree with. That even if true scientists should recognize limits of studying human behavior as long as the public has expectations, there are people who pretend or believe that they can do more to meet popular demand than what is really in their power. When we communicate scientific knowledge in these policy arenas, there's this tendency to put uncertainty to the side, the fear that if I mention uncertainty, then I'm just going to be dismissed, and it leads to kind of an overstatement of our confidence in actually what the scientific inputs are. And so what I want to get to today is, can we back off that confidence and still have very interesting and important messages to convey, and kind of what those might be. So how can uncertainty matter? And I'll be talking about this in the case of climate change. Could make us more or less proactive. One of the fears of talking about uncertainty is it's just going to lead, obviously, to being less proactive, and maybe that might be viewed as a bad outcome. I want to challenge that kind of naive, that what I think is a naive perspective. And it also may lead us to want to do things like reduce future exposure to uncertainty. Now, answers to these type of questions, I mean, is that something, what do you want to do? Answers to these two questions are going to depend in part on how much or how little confidence do decision makers have in their baseline probabilistic predictions. So this notion of confidence is really going to be important to what I want to talk about today. So how proactive we should be in the face of uncertainty. To really think about this question, to make a probe into it, I like to put on the table two trade-offs. So as economists, of course, we're talking about trade-offs all the time. In the case of uncertainty, there's two trade-offs that I think are kind of central to these type of questions. The first is, when I'm using a quantitative model, where I have multiple models, how much weight do I put on best guesses? I take that model, I can generate, here's my best guesses what's going to happen. Versus I look at that model and say, well, what are the possible bad outcomes? If I only focus on the best guesses, then there may be non-trivial possibilities suggested by that model for some pretty bad outcomes. If I only figure out what the worst possible outcomes are of models, then I can lead to very extreme type statements or frustrations. I just don't even bother getting up in the morning. Things could be so dire. So the interesting place to be is somewhere in between. And then how do we kind of think about that in between position? In an entirely different problem, if you think about pandemics, right after the pandemic was initiated, the quantitative models were and predictions were talked about in rather different ways and not always clearly stated what those were. Sometimes they're giving us best predictions, and sometimes they're giving us warnings about what might happen. Both uses are interesting, but you just don't want to go focus on just one or the other. And the next type of trade-off is important: is do we act now, or maybe in the future we're going to know more? We wait until we learn more. So this might be an argument for, well, we shouldn't address climate change now because we're going to know more about the economic damages as we in the future, and so why not wait and act then? I want to argue that, well, if you wait until too long, it might be very, very costly to act at that point in time. So maybe you want to at least do something now on the possibility of bad outcomes without being fully confident, without having full confidence in their measurement. And maybe down the road, you'll figure out more stuff, and that will lead you to do certain revisions. So these are two trade-offs that I think are really fundamental to thinking about uncertainty in policy. So I want to put on the table today 4 different channels of uncertainty that are pertinent to climate change. One is the usual one. When I write down models of investment under uncertainty, there's issues about productivity uncertainty. If I make a capital investment today, it's going to alter future output, but there's technology shocks that might affect that type of consideration. Next one is going to be geosciences. If I emit CO2 into the atmosphere today, that's going to have an impact on the future climate. There's lots of evidence of a human imprint onto the environment, into the climate system, but the quantitative magnitudes remain uncertain. The economic component of this: how will climate change in the future alter economic opportunities and human well-being? This comes under the category of damages often. The challenge here is we're potentially pushing economies into places that they haven't experienced in the past. And so therefore, it involves some type of conjectures in terms of what those damages might be, and there's uncertainty attached to those. Related to that is there's like economies are adaptive. As the environments change, the economies are going to change, and how does one really capture that adaptation? Third one is going to be a type of technology, and that has to do with ways that we can address climate change through technological advances. So that opens the door to saying, well, if I want to invest in research and development today, how might that help me, or how might that help society, or in the discovery of economically viable technologies in the future that can kind of fully replace dirty technologies with clean ones? Like an example like this would be nuclear fusion. People think that could be hugely beneficial, but to the extent it's beneficial, it's going to be decades away. So I'm going to address this problem, and I'm going to simplify things. Of course, there's very challenging problems when it comes to policy making in the climate change arena because of all the different policymakers involved, and they might have different incentives. They may face a little bit different challenges and the like. Those type of political economy questions are absolutely very, very important, and they're very critical to actually putting pragmatic policy proposals on the table. In order to understand this uncertainty channel and how it operates, I'm going to really streamline things dramatically. And this is going to be, this makes this more by way of illustration, showing you why uncertainty can be important by adopting this kind of fictitious social planner for the entire world. Okay? So absolutely, there's important things I'm abstracting from here about applied policy considerations, which are also clearly first order. But in order to feature this uncertainty channel, I'm going to simplify things along that dimension. Okay, well, think about this. Two policy levers. One is there's this is common in the literature: reduce fossil fuel emissions. So people talk about carbon taxation or with the aim of kind of reducing fossil fuel emissions. But I also want to talk about one that's been less well explored. There's been some work on this, but it's been less well explored. And that is this investment in the discovery of a new technology that's a clean replacement. And those are going to be the two levers that this policymaker is going to have at his or her disposal. So here's another kind of insight from University of Chicago. Frank Knight, who was a prominent economist at Chicago, the teacher of Milton and trainer of Milton Friedman, George Stigler, and a whole cohort of Chicago economists. Knight talked about this distinction between risk and uncertainty. And so here's like a quote from his book, Risk, Uncertainty, and Profit. Uncertainty must be taken to be radically distinct from risk. And he argues that at the time it's not been properly separated. And I think in many discussions we have now in economics, it's also not separated. There are far-reaching crucial differences in bearings of the phenomenon depending on which of these two is really present and operating. So this is really the topic I want to talk about today was certainly very much on Knight's radar screen. And I'm not saying that Knight would be endorsing the way that I'm proceeding with this, but that type of challenge has been out there for a long time. Keynes also wrote on this question. Knight's book is really well cited, Risk, Uncertainty, and Profit. If you actually read it, it's not the most coherently written book in the world, but it certainly does open the door to this important type of question. So I would argue there's been some important advances in decision theory over the last couple of decades. I've been involved in some of them, but there's been a very, very extensive literature on this. And this decision theory approaches are meant to develop and justify what's notions of rationality, or perhaps better described as prudent. Now, the kind of initial gold standard in this literature was Savage's expected utility axioms and subjective probabilities. But even Savage, my colleague here, Stephen Stigler, who's an expert in the history of statistics, has been feeding me through with a bunch of Savage's writings and exchanges, and even Savage understood that his axiomatic system was had limitations. It was probably only mostly appropriate for very simple problems, and this issue of confidence was kind of off the table. So Savage didn't necessarily think his axioms solved everything, even though that they're clearly a very elegant treatment of the problem. So anyway, there's been extensions of this approach. And what these extensions do is they allow for a more general perspective of uncertainty. Okay, and these draw from insights not only from economic decision theory, but of course decision theory's origins go back to people like Savage was a statistician. Before that, Wald was a statistician. There's been important contributions coming in from control theory and elsewhere. So there's different things that you could not know, okay? Risk is the thing which we kind of most commonly teach in our classes, and I want to think about risk as you don't know outcomes, but you know probabilities. Another alternative is which among multiple probability measures is best. I want to call this ambiguity, or from a statistical standpoint, this would be prior uncertainty. I've got multiple models on the table. They each might have different prescriptions. I don't want to necessarily go all in on just one of these models, but I want to consider looking across them. There's this famous quote from St. Thomas Aquinas on beware the person of one book. So I want to extend that to this setting to say, beware the person of one model, that in many situations, it's valuable to have multiple models on the table. The third one might be the hardest one to really wrestle with, and in many respects might be the most important one. The ways in which a model might give flawed predictions. That is, the models we write down, they're simplifications, they're abstractions, they're certainly not even intended to be complete descriptions of reality. So therefore, they're in some very literal sense misspecified. I can think, from a statistical standpoint, I think about this as a form of likelihood uncertainty. Okay? And so we use models. We think they're very insightful. We think they give us guidance, but we can't take them fully literally. And so, what are the bounds on the valuable uses of models? And that's where this kind of misspecification concern comes into play. Now, I want to use the tools from, I say, statistics, control theory, probability theory, and even asset pricing theory to do things like the following. I'm going to have these multiple sources of uncertainty. I listed 4 different channels of uncertainty. And then the question is, if I look across those different channels, which one of those is most consequential for designing prudent policy? So I want to look at this. I can have uncertainty coming from many, many different directions. I want tools that allow me, or ways to think about these really matter to the question at hand, and these are not so important. Okay? And the ones that really matter, maybe that's cases where we can kind of look more closely at evidence. Maybe that's cases in which we can, seek further expertise in the future and the like. The next thing I want to do is the other thing I want to do is construct uncertainty adjustments to so-called shadow prices. So if I think of like first order conditions and optimization problems, they often involve things like partial derivatives of value functions and the like. Those partial derivatives, I want to argue we can interpret those as a type of shadow prices. And then uncertainty is going to matter for how we construct those things. And so this helps us to interpret what the model is telling us, because as we see the role of uncertainty there, it's going to show us how these marginal valuations are shifted. And then I want to push this even further to say, well, how much should future concerns impact current prices? So this is where this asset pricing kind of type of perspective comes into play, applied to social valuation. That asset price is all about doing things like looking at discounted cash flows in the future to figure out what's going to what current valuations are. We apply those same type of insights into climate change, but making these uncertainty adjustments, and then how far in the future do we have to look in order to get the really big impacts on valuation? Finally, I want to explore the consequences of uncertainty aversion on the design of prudent policy. So I, as a researcher, it's not my job to tell society how averse they should be to uncertainty. What I can do, though, is I can show you, as I look at different aversions, what the implications are. And then we can kind of look at that and try to figure out where's a good place to be. So how do we think about this trade-off between best guesses and worst and kind of worst outcomes? And so I want to really kind of delineate that trade-off in a very hopefully useful way. Formally, how this works is you formulate a so-called max-min problem. You replace a social maximization problem by a max-min problem. And the max-min problem then becomes a game. It's a game in the kind of a simplest form. It's a zero-sum game, but you can think of it as a game between the maximization. The minimization is there to figure out, as I look across the different type of uncertainty inputs that I'm unsure about, I don't have full confidence over, which ones are most adversely impactful for that particular course of action. And then I can kind of, that allows me to define a full set of preferences through this minimization step. Now, what I'm going to do is I'm going to introduce these penalization parameters. So this is going to be a type of sensitivity analysis, okay? There's going to be subjective inputs. I'm not going to be fully confident in those. Priors, likelihoods, and the like. I'm not going to be fully confident in those. These penalizations, though, are going to dictate when I have extreme penalizations, that's going to be a statement of great confidence. When the penalizations are weaker, that's going to be a statement of less, are smaller, that's going to be a statement of less confidence. And then we've got to kind of then go through and kind of maximize over the control processes. So the minimization step will be subject to this penalization. There'll be a maximization then over the different choices that the planner can face. Now, for some of these problems, there is an equivalent risk aversion interpretation. Some of you may be familiar with Krebs-Porteous. It's often attributed to Epstein-Zinn, although I guess the origins go back a bit further. Recursive utility. There's a way I can reinterpret recursive utility as being concerns about model misspecification, and for a lot of purposes, I find that the more useful interpretation. Valuation. It turns out that this minimization problem that I'm solving, if I take that minimization problem at the optimal solution, that gives me a measure, a probability measure that I can use for representing valuation. So this probability measure comes out of a minimization problem. It's not a statement of your belief. It's a choice of a probability that allows you to implement a more type of robust approach to decision making when you're not fully confident in your inputs. Okay? But it turns out that you can show that minimization gives you a probability measure to use in valuation, and that probability measure is the one that adjusts for your aversion to uncertainty. So the minimization actually helps us think about these kind of first order conditions and how they operate. Much in the way when we make changes in probabilities in order to do valuation in finance. It's a different type of change in measure that shows up in, say, derivatives claims pricing, but the mathematical tools are very similar. As I say, as external analysts, then we'll explore the sensitivity of this minimizing distribution. And for some problems, there's this important distinction between model misspecification concerns and ambiguity over the subjective inputs. And one can confront this with two distinct forms of penalization. For today's talk, I'm going to focus on the former, in part because the two don't have have kind of similar implications for this particular problem. For other settings, some work from Sargent and myself has shown that they can have really very, very different implications. But for today's purposes, that distinction is not going to be so important. Here's some papers I like. So now let me go to this uncertainty aversion and robustness. As I indicate, I want to borrow insights from derivatives claims pricing and the like, and from robust Bayesian decision theory to do the following. When I'm setting these penalization parameters, you might say, well, how do you set those? Well, what comes out of the insights from robust Bayesian theory, going back, all the way back to kind of a guru of robust Bayesian methods, Irving Good, is you take that kind of minimization step, you look and produce that probability. So you just think about that penalization as a way to get you this worst case probability distribution, and then you look at that and say, is this really something silly to be guarding against? If that worst case outcome looks so extreme, then that's the kind of don't get up in the morning solution. But as I make that penalization more and more severe, you're pushed far away from that. And so now we can do this inspection, and then we can kind of produce these worst case distributions, which I'll be doing for you, and saying, well, are these modest, or are these or are these looking extreme? So it's kind of mapping between these worst case probabilities, and this penalization turns out really important in what we do. As I indicated, I want to use the uncertainty adjusted probability measure for social valuation, instead of market analogous to what we do in market valuation. And then I can represent these social valuations with this. So I'm going to use this decision problem to really think about which source of uncertainty is consequential. Okay? So I'm going to be doing, I'm going to look at these 4 different channels of uncertainty. I'm going to do the following. I'm going to say, well, I'm going to activate each channel by itself. Productivity, geoscientific, economic damages, technology. I can operate each one separately, and then I'm going to operate, and then I'm going to do them all simultaneously. Okay. From there, I can figure out which of those channels really is the one. When I look at things simultaneously, which individual channel is closest to what I look at simultaneously, and that's going to kind of tell you kind of which of these 4 sources really matters. Okay, and so that, and some problems that can really stand out, and other ones you might find that all 4 really contribute, symmetrically to the problem. And in today's talk, is going to turn out that one's going to dominate. Okay, the other one is I've already hinted at. I'm going to depict prudent valuations as dependent on prudent decisions as dependent on marginal valuation. So just think about first order conditions and optimal control problems. You've got partial derivatives of value functions being linked to optimal decisions. Think about those partial derivatives as the counterpart to these marginal valuations. I want to think about these marginal valuations as asset prices with uncertain social payoffs. And now I can look at the components of those marginal value, those stochastic payoffs. They can be stochastic costs, stochastic benefits, and then split them into distinct components depending upon their sources, and kind of also get decompositions that are revealing to how we should confront uncertainty. So if I think of these marginal valuations, in the case of climate change, 2 come to mind: the social cost of global warming. So one of the state variables in my model will be temperature. So the marginal valuation of temperature gives me a type of social cost of global warming. From that, you can map directly into the implicit measures of the social cost of carbon, often discussed. The other one is going to be the social value of research and development. So if I invest now in terms of expanding my knowledge stock, that knowledge stock can lead to potential discoveries of economically viable clean technologies in the future. Then that's going to be that's going to apply the stock of knowledge as an interesting social valuation. Yeah, here's some other papers I like. I'm not going to get into it today. So if you think about risk components, the model I'm going to be writing down, it's kind of convenient to write it down in continuous time, but we can think about there's 2 different sources. We have small shocks and big shocks. The small shocks are these normally distributed shocks. They're in a model of Brownian increments. The big shocks are Poisson events. There's these big Poisson events. Okay, and there's going to be 2 different types of Poisson events. One is the following. I'm going to get this trade-off between acting now versus waiting until we learn stuff. So one possibility is as we start, right now, the climate change damages are arguably somewhat modest to economic opportunities. The concern is down the road they might be much more severe. Well, maybe as we start damaging the climate system more and more, we'll get a better read on economic damages. So maybe in the future we're going to know a lot more about economic damages than we do now. So now we're quite uncertain. In the future we might know a whole lot more. So I'm going to capture that by a Poisson event. This Poisson event is going to be triggered by global warming. So as we warm the as we warm the Earth more and more, at some point in time, it's this knowledge about that damages as we go to more extreme temperatures will be much more self-evident than is right now. And we're gonna have that Poisson event get triggered somewhere between 1.5 and 2. Climate scientists often talk about tipping points. Well, we don't want this tipping point to be a situation in which the world ends, but the tipping point for us is going to be, it's going to reveal something about the damages in the future and kind of how severe they are. The other one is going to be a discovery of a new technology. So I'm going to have a very specific type of technological discovery here. And we've got work doing other forms. It's going to be a big discovery one. So I invest things. I can invest in this in the stock of knowledge, and then down the road I figure out this brand new economically viable technology that gets us out of climate change. So I'm going to treat that as a big event. Alternatively, one can certainly think of models of technological advance, which are much more accumulations of a bunch of smaller events. But for us, it's going to be a big event. It's going to be a big discovery. It's going to be, arguably this is something that would require some government support early on, as has been happening in the case of nuclear fusion. Down the road, it may be more and more possible to offset it to the private sector as the economic viability becomes more self-evident. Although even now there's venture capitalists very much have nuclear fusion on their radar screen, even though it's decades down the road before it has a chance to be economically viable. Then when I put, these are the sources of risk, these big events and small events, Brownians, Poissons. I'm going to relax full confidence in order to explore the sensitivity to misspecification. So for the Brownian uncertainty, then I'm going to take this kind of Brownian motion and replace it with a Brownian motion with a state-dependent drift or local mean. So in discrete time, think about there being these normally distributed shocks. I'm going to stick a mean in there, but the mean can be fully state and history dependent. So it can depend on a lot of stuff, and it allows for different forms of misspecification disguised within this normal shock. The second one is going to be these Poisson events. Now, Poisson events are typically modeled by these so-called jump intensities. Okay? The jump intensities, when the jump intensity is big, the Poisson event is more likely to be triggered. Okay? And so what's going to happen then is the way the misspecification concerns will play out is you're going to rescale these state-dependent jump intensities. You can allow them to be bigger or smaller, depending on whether it's a good event or a bad event. The damage discovery is going to be kind of, if it happens early on, it's going to be a bad event. The technological advance is going to be a good event. So let me just sketch pictorially how the model works. I'll fill in a few more details, but I'm going to not go through the detailed equations. I'm going to start off with a model that's pretty much simplified standard macro growth model. Okay? It's literally an so-called AK type model. There's going to be capital. The capital gets combined with the capital broadly conceived to include human capital. Capital then contributes to output, as does energy. Okay? You take the output, you split it between consumption and investment. In this economy, then, Adam Smith's invisible hand are going to work just fine. There's no externality. There's no reason for policy intervention. The planner problem I saw would be one that would be fully decentralized by private markets. But okay, next I'm going to add in this. Next we can put in this externality. So as energy input at the same time is going to lead to these carbon emissions. That's going to change the climate, and that's going to impact economic damages. So economic damages are going to be a function of how much you warm the earth, and as well as this notion of a tipping point that can kind of trigger more extensive damages in the future. That can affect economic well-being. You can think about this as the damages here as a proportional reduction in the productive output of the economy. That's going to turn out to be a convenient way for us to model this. Finally, I want to add in the possibility of taking some of that output and investing it in R&D. The R&D down the road can lead to a new clean energy source that can offset the the externality from climate change. So that's basically what's going to go on the model. It's going to be an AK model with adjustment costs and a dirty energy input. Output, as I indicated, gets splits between productive capital investment and R&D, knowledge capital, and consumption. The climate externality is going to be a proportional reduction in the production capacity that depends on a temperature anomaly. So here's some of the uncertainty inputs which I put into our analysis. Let me start from the climate side. Okay? There's divergent climate model predictions, and the climate models are highly nonlinear models. We couldn't start putting a bunch of these models inside an economic model and have anything that was remotely tractable. But climate scientists have figured out that some of the outputs of their model, even though the models are highly complex, have a relatively simple structure. And roughly speaking, if you emit carbon into the atmosphere, and that leads to temperature changes, and that impact leads to a kind of a proportional relationship between emissions and temperature. Now, for climate scientists, these are transient responses. Transient for a climate scientist is very different than for economists. For a long-term, for a climate scientist, it's something that extends over many, many centuries. If we think of our models, economic models are good enough for, can work over like six or seven decades, we're happy. So what happens is that that proportionality relationship kind of holds over the horizons that we really care about. Now, the way that climate scientists will sometimes do model comparisons is the following. You'll go to different model groups to say, well, take your baseline, give your model a emissions pulse, and tell us what's going to happen to the temperature. Okay? So we give all these different model builders the same type of hypothetical experiment, have them then report what the outcomes of their models are to do comparisons. And if you look at those impulse responses that really don't include this kind of tipping point behavior, but what they show is the following: is that with this over an interesting range of pulses, what happens is you get a buildup of the response, of the temperature response over the course of a decade, and then it flattens out. So it's extended over many decades after that. And so all the models kind of have that similar, very, very similar pattern. There is an initial period of buildup, but by 10 years, then it's flattened out. But they flatten out at different places. So what I'm showing you in this histogram is just a summary of the model output of how it flattens out. Okay? And so I'm going to call this climate sensitivity. It's not the same language that was used in some of the climate change literature. So their notion of climate sensitivity is much more long-term. So what this comes from is 144 different models. The models, some of these models are models that tell us emissions to carbon in the atmosphere. Some are carbon in the atmosphere to temperature, and then we look at the different combinations. That gives us 144 of these, and I've got this kind of histogram of the responses. Now, if I want to turn that histogram into probabilities, one way to do that is to say, well, every model I'm going to assign the same prior probability to. So probability 1/44 to each model. Then that histogram becomes a set of probabilities, and that might be a baseline set of probabilities, but maybe you want to kind of ask if whether that's the right weighting scheme to be doing or not. Okay. Now, I indicate there's unknown timing magnitude of two events. One, there's this tipping point in the climate economic system that reveals damages, and the other is a technological breakthrough. The likelihood of the first is increased by temperature increases. The likelihood of the second by investment in R&D. So the way this model of damages is going to work, in order to get this trade-off between acting now versus waiting, there's going to be this Poisson jump process. The jump intensity is going to increase over the temperature anomaly between 1.5 and 2 degrees. By 2 degrees, it will have been realized, but it will not happen before 1.5 degrees. At the time of the jump, the damage curvature for more extreme temperatures is going to be revealed. And that tail curvature coefficient is going to take on one of 20 different values. So there's debates about how steep damage function should be. We're going to allow uncertainty over that, but that uncertainty is going to eventually get resolved. And so here's how it's going to work. Suppose this event gets realized at 1.5. At that point in time, then we start off with these very modest damage curves. At that point in time, more curvature kicks in, and it's kind of given by the red solid line is the kind of mean across all possibilities. The lower envelope the lower part of that envelope tells you the lowest curve, and then then the upper part of the red ones is the upper point. So like Weitzman has argued for much more extreme curvature based on part of uncertainty. Nordhaus's have generally been much more modest. Now, this event could occur at 1.5. That's kind of bad news because to get this more extreme curvature, it could occur somewhat later. It could occur all the way as late as 2. So at 2, this curvature kicks in. It becomes more severe, but the severity is going to show up at kind of bigger temperature anomalies. Again, there's going to be a range of those curvatures, whether it's steeper or more flat, or will they get revealed. So these are these proportional reductions in output. There's uncertainty today, but eventually it's going to get resolved. It's going to be in one of these, and you're going to know what this damage curve is eventually. Now, the other one is just going to be the single discovery of a technology. So there it's all just in the intensity. So what our initial research has shown, is the following. When you put these 4 channels of uncertainty on the table, it's the unknown timing and success of research and development investment that is the most prominent contributor to uncertainty in climate change economics policy. Lots of discussions of the social cost of carbon don't even have this channel on the table. For us, it's the most important one. Now, the other thing that's interesting here is that source of uncertainty in our calculations leads to doing more green R&D investment rather than less. So you really have lots of uncertainty about this R&D investment. In spite of that uncertainty about what's going to pay off, in spite of that uncertainty, that uncertainty you have, it's going to lead you to do more investment. Now, this uncertainty is a notion of uncertainty aversion. It's not that, I've got more variance, there's this upper tail that I can exploit, as sometimes shows up in option calculations. It's that's not what's going on. This is making the decision maker more unsure about the prospects of things, and it leads to more aversion. Okay. Now, this source of uncertainty is very important for determining the magnitude of R&D investment. You still want to reduce emissions, because by reducing emissions in the short term, that's going to allow R&D to have a chance to be a better chance to be successful. This response turns out to be less sensitive to uncertainty. This is in part due to the fact how inelastic energy demand is in our production functions, but you still want to do these emission reductions. So what I want to spend a lot of time on is this second point here. Why would you want to do more rather than less? Because that's not at all obvious, and in fact, there's two competing forces in play there that I want to talk more about. So let me just show you the type of predictions, the type of output that comes out of this model. I can do this for temperature. I also, of course, we have plots for R&D investment and for other and emissions and the like. Okay? The model has these small shocks and it has these big events. Okay? So what I'm just going to show you is how temperature behaves. Recall by 2 is the place where this by temperature anomaly 2, the more extreme damage curvature has been revealed. Okay, here, and I'm just going to show you 5 paths. Okay, the model has these big and small events. So given that it's not obvious what the right probabilistic way to characterize the outcome are. But so I'm just going to show you the type of paths that can occur. So this is one in which neither big event gets realized. Okay, which is possible. There's been no realization of damage. I haven't triggered the damage curvature, nor so I still don't know about damages, and I still don't know, and I still have not had the technological success. Things gradually warm here. There's kind of no news here of any type. The second one is one where there's good news about future damages. This is path 2. So path 2 for stochastic reasons is higher than than the blue path, but that just has to do with how the small shocks play out over time. That's a kind of a random occurrence. At date 28, you get the damage realization. But the realization here is not a big event directly on things like temperature. It's just telling you about how temperature will be responding in the future to more to more emissions. And I'm sorry, it's going to tell you more about how damage is going to respond in the to future temperature increases. So at this point, it's good news about damages. Damages aren't quite so severe. So if I actually showed you the plot here of emissions would now you're actually less fearful of emissions, and you might well reduce your R&D investments because climate change is not as bad as you feared that it might be. Here's one where there's bad news about future damages, but that doesn't occur until year 37. So at year 37, you discover this damage curve, so you have a lot more information. Since it's bad news, you start reducing you're more aggressive at reducing emissions, and you might be more aggressive in terms of investing in R&D. Other paths are the discovery paths. So here's a discovery path at year 25. You discover this new technology at that point in time. Since we're only looking at temperature coming from climate change, damages coming. We're only looking at the temperature responses to emissions. The temperatures flatten out here. Of course, temperatures will fluctuate for other reasons. And so there's no more global warming takes place because of this discovery, or it might happen at year 20, and at year 20 the temperature levels out. Okay? So that's how the model plays out. There's these small events accumulated to these different trajectories, and then these big events will then will affect some of the outcomes in more important ways. Okay, so to understand this question, why do you really want to be more proactive? And by being more proactive, it's really quite substantial. And for what I think of as modest uncertainty aversion, you end up doubling the amount of investment in R&D in some of our baseline calculations. So let me just talk about this asset pricing view of social valuation, marginal social valuation. So I'm just going to start off with some simple Markov process in continuous time. There's discrete time counterparts to this. Just think of this x variable. It's evolving according to what's called a diffusion. It's got these. This should be. It's going to depend on little x, or should actually be x sub t. And there's got the state dynamics for the mean state dynamics, or it's these local mean effects, and then there's this exposure to this Brownian increment that could also be state dependent. Yeah. So W here is just this multivariate standard Brownian motion. So basically, this is a model which only these normal shocks. The normal shocks can compound in nonlinear ways. That's because of the nonlinear transmission mechanism. But the inputs, the exogenous inputs, are these local normal inputs. Okay. Now I want to construct a stochastic impulse response as measuring an impact of a marginal change in the state. So I've got these state dynamics, and what I want to do is ask, what happens if I move each of these states a little bit at date 0? What happens through the trajectory? It's a stochastic system, so how it's going to move is going to potentially be stochastic. So this is going to be close to, there's lots of macroeconomic research on so-called impulse responses. These are going to be very close to impulse responses. Since it's a nonlinear system, I'm going to make them marginal changes. Okay? And it's going to be a central input in a margin evaluation. So how do I do that? Well, there's a convenient mathematical way to do it. It's called, there's construction of so-called variational processes. They're going to give you these basically stochastic impulse responses to small changes in states. That's that. And then what I'm going to do is I'm going to introduce a process of the same dimension as x, Okay? But I'm going to initialize it differently. If I initialize at each of the different coordinate vectors, I will get a marginal response at each of the different states. So wherever there's a 1 in that initial condition, that's going to tell me the state over which I'm looking for the marginal impacts over. Okay? And now the question is, how do these lambdas behave? Okay? Because they're going to be important inputs into the analysis. These are going to be kind of stochastic versions of these impulse responses. So you can work this out for a nonlinear system. The somewhat perhaps slightly intimidating equations here, or tedious equation, whichever way you want to look at it, is really nothing more than kind of doing the chain rule. The system's stochastic here, and to actually do this formally, there's a theory of so-called million-wall differentiation that comes into play. But roughly speaking, what you're doing is the chain rule here. I want to look at the evolution of this, like d lambda, the ith component of I. I'm going to go to that ith equation. I'm going to differentiate that with respect to xt. Xt is the current state, but then I need to see how the current state responds to what I do at day 0. And that's where the lambda t prime comes into play. Same thing for the weighting on the Brownian shocks. So basically, I construct this this new process. It evolves as a function of the original state variable process, constructed in this somewhat rather straightforward manner. Now, to study these marginal responses, to do this kind of nonlinear versions of impulse response analysis, then I would have to study the joint dynamics of the original state vector process and these marginal responses, these marginal impulse responses. Okay? And that equation just tells me the dynamics. Now just observe one thing. Suppose that mu happens to be linear in the state. Suppose that sigma is constant. Okay? This would be a case of kind of the plot process that would be globally normally distributed. Okay? And so this would be like a linear vector autoregressive system. In that set of circumstances, lambda is non-stochastic. So when we're looking at linear systems, local impulse responses and global ones kind of all line up because of the linearity here, and these objects, these marginal responses are non-stochastic. And so this would then replicate, solving that equation system would just replicate what we do with impulse response analysis. This is a nonlinear stochastic process, so that means the variational process is also stochastic. Okay, so now I'm going to assert, this requires some actual demonstration, kind of keeping track of various different partial derivatives and kind of some valuable bookkeeping here. I'm going to assert the following. If I want to interpret the partial derivative of a value function, okay, I take the at a given state. So I take the value function. A value function is just a discounted expected utility function. I want to compute that. I want to look at the derivative of that value function. I claim that's going to be representable like an asset price. Okay? I'm going to have subjective rate of discount x minus delta t. The delta out front is just a scaling of the instantaneous utility function. Okay? Then what I'm going to do is I'm going to take the partial of the utility in the future with respect to the state. That vector, dot that in with this stochastic impulse response, telling us how to go from 0 to t in a stochastic manner. Form that expectation. Then this representation holds, and as that lambda 0 set to each of the different coordinate vectors, I've now got a representation for all the different derivatives as this expected discounted value. Okay? Now, the expected discounted value, the object in there is this partial derivative of u with respect to x dotted in with lambda. Now, those of you who are familiar with asset pricing, we often talk about marginal rates of substitution, marginal utility valuation. Well, you could take the partial u with respect to x and express it as partial u with respect to consumption, and then consumption times consumption with respect to x by the chain rule, and get a representation of that form as well. Okay? So this is a very intuitive formula. It takes a little bit of effort to produce it. but it's very useful for interpretive purposes. So this is a sense in which this partial derivative gives me a type of marginal valuation. I'm looking at the discount expected value, and since and now I can take the contributions here coming from the different states in these lambdas, and I can start decomposing things. So I can use these same type of decompositions we're familiar with from macroeconomics, but I can use them to study these valuation problems. Okay? That's the idea here. There's, of course, this is a nonlinear problem, and it's very important that these impulse responses be stochastic in nature. Okay, now if I want to add in this kind of concerns about misspecification, reason robustness concerns, or these more general uncertainty aversion concerns, I do the same formula, but now I change that expectation to be the one under the minimizing probability distribution, and this formula continues to apply. Okay? So that's a very handy way to proceed. This type of representation is, some of you may be familiar with co-state equations that often show up in dynamic control. If I look at the co-state equation here, that's a full vector system, and it's hard to interpret what the joint solution of that is. And these type of representations, I think, are much more intuitive and then useful to interpret. Okay, now the model that I described are one with these big Poisson events, so I have to do something about those. Okay? So let me talk about what I'm going to do about those. I'm going to imagine having this nice small shock type evolution until a big event occurs. Right? I'm going to think of that big event as like the equivalent to a terminal condition. If I'm solving some type of consumption savings problem with over a finite lifetime, there'll be some type of bequest function which I have at the end, and that bequest function can be state dependent. So I'm going to think about what happens at the jumps as giving me a bunch of continuation values conditioned on the jumps. Right? And I can't think of those as playing the analogous role to these bequest functions. So I can use that same formula now, but I just turn it into a finite horizon problem going up until the point of the jump. Then what I plug in is the endogenously determined continuation values conditioned on the jumps happening. That's the perspective I'm going to adopt here, and then I can just, with some modifications, use that same formula which I just showed you. So here I'm going to have, I talked about two different types of jumps, damage jumps and technology jump. Now I'm going to have a bunch of damage jumps here. I'm going to record them as different damage jumps because I'm going to list the different damage jump for each different possible damage curve. Okay? So actually there's going to be 21 different possible places one could jump to, because there's going to be 20 different damage curves, and then there's this technological discovery. So I'm going to have jump intensities here of I'm going to have 21 different jump intensities here. 20 of them have to do with damages. One has to do with this technological advance, this technological progress. Okay? So I'm going to have these intensities, and then I'm going to have these continuation value functions once a jump takes place. So when a jump takes place, I go to a jump of type L. I've either had a technology discovery, or I know what I know the damage curves in the future. Then I'm going to compute a new value function condition on that. Okay? And I have to take that one step further because it's another jump that can occur. So So it's kind of backward induction across these jumps in some sense. Okay, but I'm going to take that back to the initial period before the first jump. So that's how it's going to work. Now, because of these jump possibilities, that's going to change that discount of what we're discounting. Okay? So there's two adjustments I'm going to make. Okay? The first is a discount rate adjustment. I'm going to have to adjust that discount rate for the possibility of a jump taking place. So I'm going to have to adjust for jump probabilities. That's where these jump intensity comes into play. There's capital L of them. Now I've stuck in this G star there. Why is that? That's the minimization. That's the outcome of the minimization. The big J super L is the baseline. The little G super L, G sub Z comes out of the minimization. Okay. So for technology, you would reduce a little bit the amount of that intensity. Okay. So the G's are these uncertainty adjustments. For damages, it could be just the reverse. Now for R&D then, this lowering is going to make, of the intensity, is going to delay the success. The fact you're delaying the success of R&D, this channel, this effect here is going to make R&D investment less attractive. So this force is going to work against being more proactive. Why? Because, well, you're not sure about when this is going to pay off. You're going to make this cautious adjustment that's going to be implemented by putting these G's that are less than 1. Okay. So let me show you how these intensities work. I'm going to start off with a baseline here. Okay. And I'm going to, instead of showing you the intensities, I'm going to show you what happens about the timing, the timing of the event happening. So if I take the damage event, okay, I'm going to lump all the damage jumps together because those events all get realized at the same instant. Okay. What happens is, the way that we've set it up is that tends in our kind of planner's problem, the peak probability of that is occurring at year 30. Okay. Now, neutrality means that I don't care about this. I'm fully confident in my model, and I don't have any ambiguity or uncertainty about the specifications. That's the red line. The green line is going to make it more peaked, and the blue line even more peaked. Interesting here, it's not really affecting the timing of the damage. It said that the damages are still centered around 30. Now, why do those go down as you become more? Why do those go up as you become more averse? That's because we know for the other one, for the timing of the technology success, those are going down. So those going down, that probably diminishing is what's showing up in this bottom plot here. Okay. So that's then showing that. Right. So that's giving you the probability distribution for the what's going to happen for the first jump. It could be technology, it could be damages. If I kind of sum these two things together, then you have the combined probabilities. Okay. Damages are nothing's going to happen until you get to a threshold of 1.5 in our model. That doesn't occur until after 15 years or so. Before that time, it's only damages that occur, and then eventually the event that becomes very, very likely is the damage event, and then the technology event gets pushed off into the future after the damage events are realized. So this just shows you the type of probabilistic adjustments you're making here. I would argue that they're not extreme, but of course you're seeing much bigger ones. Proportionally, you're seeing much bigger ones for the technology adjustments. Okay. Let's see, just a minute. So before once I include these jumps, then I'm going to have to change that flow term too. Okay, I already showed you that you got to reduce the probabilities. But now I also have to make an adjustment to the objects that I'm discounting. So the marginal utility one, which you had before, that's this kind of stochastic discount. That's the stochastic response dotted in with this partial derivative of the utility function. But now there's some more terms that show up here. Okay. The first is the marginal impact of a jump here. So the jump intensities depend on state variables here, and that dependence is very important. So when I'm differentiating through to get equations for these marginal valuations, the partial derivative of these intensities shows up here. In the absence of any type of aversion, they show up with the neutrality formula. With the aversion formula, you make this kind of concave adjustment to that. So under neutrality, what you do is you look at the difference between the value function today, that's v, and the one you jump to, v sub l. So that difference in value functions contributes a flow term to the it contributes a flow term to this asset valuation formula. So what happens here is you go into your optimization problem, you've introduced a kind of adjustment for jumps, and now you look at how that plays out in terms of these asset pricing representations, and that's what shows up here. When you reverse, you make this kind of concave adjustment here. The concave adjustment also kind of works against, makes you want to be a little bit less proactive for given continuation values, but the continuation values are not fixed here. So finally, there's the marginal impact of when you jump. So when you jump, so here I've got the intensity formula here, but what I'm differentiating is the value function, the continuation value function, the V sub L's. Now, we've already got a representation for the initial V, so in fact I can repeat the same decompositions for each of these V sub L's if I so desire to try and interpret the marginal impact when you jump. So now there are these different flow terms that come into play here, but this second flow term has to do with your continuation values. You're looking at how intensities depend on states, but you're also now looking at what happens when these events get realized. Okay? And that's reflected in these endogenously determined continuation values. So the second contribution here is going to be really important in our calculations. Okay? So let me just show you what happens. So there's different ways to decompose these flow terms. First of all, the first one I'm going to do is by states, okay? I'm going to do a marginal change. I want to be looking at what happens when I do a marginal change in the stock of R&D, because that's the one that affects the first order conditions for investment in R&D. Okay, so that's a marginal change I'm making, okay? But R&D is going to affect other state variables. It's going to affect capital. It's going to affect temperature. The effect on temperature is minimal, but the effect on capital can be quite important. This is going to give you that flow, the expected flow contributions under aversion. I'm sorry, for capital and for R&D under aversion and neutrality. Now, what you want to see here is under aversion, those flow terms are now getting much bigger than they are, especially for R&D, but also for capital. They're getting much bigger. So this is the term that's evidence that the flow terms are offsetting these more cautious probabilistic adjustments. What's happening here is that a technological discovery here is going to eliminate a lot of uncertainty, and that's going to lead to much better changes in continuation values. So it's the success. It's the endogenously determined payoff to success that is also moving, given this uncertainty aversion. And when you're more averse to uncertainty, that success becomes a much bigger deal. Okay? And that's going to be the kind of story behind why you want to do this, being more proactive in terms of the R&D investment. That's going to offset this other channel. So this is the contribution by state Here's the contribution by these different terms to the different components here. The marginal utility term, the marginal impact of a jump, and the marginal impact when there is a jump. So you see that up until there's a jump, the marginal utility contribution here is really quite tiny. It's both under neutrality and aversion. The marginal impact of a jump is already quite prominent in the green line. It's a little bit bigger. Okay? The red one is a whole lot bigger. Okay? So the red one is this marginal impact when there's a jump. So remember that this is the one that depends on the partial derivative of the value function when you jump. Okay? So we can start asking what's contributing to that red plot. So this is occurring because remember 30 was about the peak date it was about the peak of the distribution of when a jump takes place. So that's being tracked by this third term here. Okay? But now let me take this one step further. When you jump, okay, from that point on, there's a partial derivatives here. You want to see what they're you want to decompose those by states. Okay? Now, when you jump, so the peak jump is about 30 years. So now I'm looking at payoff contributions 30 years and out and further out. So at that point in time, this capital and R&D channels kick in, and so here we're getting about between 70 to 75% from R&D and about 25 to 30% coming from capital. Okay, so and this just shows you now we're talking about stuff that's going out 50, 60, out 80 and 90 years into the future, making important contributions into these valuation calculations. So I guess there's 2 points here. One is the future really matters here. This stuff isn't resolved by year 30. I think that the stuff well beyond 30 is important here. Moreover, there are these two forces in play here. Okay? There's two offsetting effects. The uncertainty adjusted probabilities, those are going to push the prospects for successful R&D into the distant future. That's going to make you not like this investment as much. However, when there's a success, the continuation values, you've resolved a big chunk of uncertainty, and the differences in those continuation values now becomes much larger. Implicitly, the payoff to the success is much bigger when you're uncertainty averse. The second one dominates over the range of uncertainty aversions, which we consider. So these kind of asset pricing type methods, these marginal valuation methods, help us understand these two different channels. One's coming through that endogenous discounting channel, the other's coming through that payoff channel. And that second one dominates some of our calculations. Were we to make our planner much more averse to uncertainty, the first one would eventually dominate. Okay, so let me conclude here. Sometimes the best response to uncertainty is to be more proactive. Extensions or refinements of uncertainty quantification I've described here, I think have much more general applicability. I talked about two things: how to take these multiple sources of uncertainty, figure out which ones are most potent, and then to do this kind of marginal valuation decompositions in order to understand these different contributions to the social payoffs when I'm doing marginal valuation. So for us, this is a research as part of a larger agenda to explore uncertainty impacts for both private and public sector decision making. Thanks. That's what I got to say, and I'm glad to take any questions.
Thanks so much, Professor Lars. We have time for questions. So I would like to start with. So we started your presentation saying that you use a recursive approach. So you take the minimization probability, and then look at 4 different problems, and in the end you focus on the type of ambiguity aversion and neutrality. You know that the society at times may choose a policymaker that behave in a prudent way, like ambiguity aversion, and you compare with neutrality. But you know that some policymaker may be ambiguity seeking, in a sense that towards ambiguity, they may look at the more favorable probability of distribution to justify our action. Do you think that you can extend your analysis or to the case also in which you consider ambiguity seeking and then compare the results about capital R&D?
Yeah.
Thanks.
Sure. Okay, so the perspective I adopted today was more of a normative perspective. And from a normative standpoint, I think the aversion one is the story is the one that's more easy to rationalize. However, if you want to shift this to more of a positive model of policy making, instead of saying, well, this is what we should do, maybe this is what certain policymakers will choose to do. In principle, these type of methods could be used to try to model the excessively optimistic policymaker who thinks by selling optimism it's easier to get elected and stay in power and the like, and here's the way that person might proceed. Here's the optimism that might give us the biggest impact. I haven't thought hard about that, but in principle, I guess that might help you as a more positive theory of some aspect of policymaking. Good question. I just haven't thought much about it.
Oh, thanks.
But I do think you need to have to shift from normative to positive perspective, and then that becomes interesting.
Okay. Any other question? Okay. Thanks so much, Professor Lars.
Sure.
So I would like to thank you a lot in this joint session between Unpacking and SBE. So I'm closing this presentation. Thanks so much. Thanks so much, Professor.
Yeah, I'm trying to figure out how to close out of this. I'm sorry, just a second.